Okay, so welcome everybody to our series Programming Principles. And this time I'm going to be talking about pure functions and immutable data structure. So without further delay, let's jump straight to the definition of pure function. So we'll explain first what the pure function is, and then we'll get to the why part. So pure function is deterministic in a sense that for same input always provides same output. So it's kind of like in mathematical world where you provide an argument, which is an input to a function, and it returns a return value, which is an output. So I can call this function as many times as I want. It always gives me the same output for the same inputs, and it should always return. So this is another property of functions, which is called totality or a total function. So it always returns. So what this means is that there's no access to external state outside of the function. So all the logic in the function is around the input parameters, their processing and returning the value, constructing the return value. So what this means that the function doesn't have access to the external state. So there's no user input or IO read. IO means like a network access or file system. And there's no access to global variables or basically variables outside of the scope of the function. There's no access to random values because random values are usually based on some operating system level functions that depend on hardware, and there's no even read of system type because this can change, of course. So if I based my logic around the system type, then it could return for the same input, can return different values, of course. So in that sense, functions using, for example, random values or system time are not pure. So the basic property of pure functions is something what's called a referential transparency. And this means that I can replace a function call with the return value, and the behavior of the program wouldn't change. And the pure function doesn't have any side effects. So a side effect is a term usually used in functional programming, and it describes an effect on a side. So not only that the function returns some value, but it mutates or accesses an external state. So for example, it writes to IO, it writes to database, it writes to file system, it accesses like state outside of the function. We'll get to the examples a bit later. Or it's mutating arguments. So if I provide an object to a function as a parameter, and I mutate the object, I'm basically changing the state on the heap in those languages that or runtimes that support heaps, like memory, where their memory model support heaps. There's a word about exceptions, like if a function throws an exception, is this pure or it's not? So I think that it depends on the type of the exception, because when the exception is encoded into the signature of the function, and it always, and the exception is thrown always for the same parameter, then it's like deterministic in this sense. So I consider these types of exceptions being, they wouldn't break these laws that would make the function pure. So these are things like array index out of bounds or division by 0. So if I provide a parameter with an array and an index, and I always pass the same array, the function, with some index that it's out of bounds, I always get back the same function. So it's kind of like a functions having the types of return values, and there's a way to encode errors with algebraic data types. So it doesn't have to be using the throw mechanism, but it can return either a value or an error. So these are things that we talked about in our previous sessions. But then there are exceptions that are definitely not pure. So if there's some IO access and the IO can fail, of course, we might not have a network connection, and it would happen randomly or not always, right? So these exceptions will make the functions not pure. All right, so let's get to the examples. So I'm using here TypeScript code, and this is a pure function. This is like an arrow syntax of defining functions. So this one's pure because I'm accepting two parameters, an and a2, a1 and a2, and I'm returning a string, which is just a string using those parameters. So this function is really pure. It doesn't have access to anything outside of this function. On the other hand, look at this function here. So who is your father is a function that accepts a string parameter and returns a string. But the thing is that it actually depends on some variable outside of the scope of the function. So this means that this is a closure around this scope. And when this changes, some global var, the behavior of the function changes. It returns a different string. So this is not a pure function. Here's a class. So class methods are inherently, by their nature, they're not pure because they access like internal state of the class. Right. So if I call the sum method many times, the result depends on the state of A1 and A2. So I can't use that referentially transparent thing to call this as many times as I want, and I would get the same value. So if you look at what is a class? Class is just a bunch of fields and functions closing over those fields. So these are really closures, but the class is like a module having a bunch of functions closing over the internal state. So that's definitely not pure, but it's like, of course, the intention of object-oriented programming is not having pure functions. So let's look at this example here. We have a function happy birthday that takes in a person. So we have a type person. So I'm providing an object of type person, and I'm returning a person. This is the signature of the function. Now what it does is it mutates the argument. So this is what I talked about, that this mutates the state on the heap. And actually it also returns the person. So it's not pure because it mutates the arguments. And it's quite kind of misleading because it's returning a person. So if I didn't see the body of the function, I would expect probably that the function would copy the person. If it returned a void, it would be obvious that it does some side effect. Because a function returning a void that doesn't do any side effects does nothing, right? So this is kind of misleading, and there are examples in JavaScript, like array sort and array reverse. It actually mutates the array and returns the array. And I created a bunch of bugs because of these quite misleading signatures. So they are definitely not pure. Now, let's talk about a bit about why we want pure functions. So I think the argument number one is readability. So if you look at the code, if you look at the function and what it does, like what's the logic in there, you try to understand it. I think it's much easier if you have everything on your plate. So there are no external references to class fields, to some variables out of scope, to global variables or anything else. Right? So this is really important. And not only, well, your IDE may help you, so you can jump through the code quickly. But in other environments, like if you're doing a code review on GitHub, for example, you can't use that go-to references, right? So you have to look it up, like what it does, what it mutates, what state does it use, and so on. So they are reusable and refactoring friendly. Really, if I have a function that depends just on the input parameters, then I can just call it from anywhere else, right? I can pull it out of scope. I can use it in different occasions. I can move it around freely. They're easy to test because I don't have to mock up like environment around that function. So if the function depends on some other functions or services or some other state that it's not directly in the function, I have to mock it up around that function, and only then I can test the behavior, right? So the testing is really easy with pure functions. I'll provide everything as a parameter. And another story is about performance. So that referential transparency property of pure functions is really important because, as I said, you can call it as many times as you want with the same parameters and it would return the same value. So this means once I get the value, it doesn't have to compute it again, right? I can cache it and use it on different occasions. If the computation is, for example, heavy, I can easily cache it and the program should behave properly. They can be optimized by compiler. They are easily parallelized. So again, if the function doesn't access like external state or mutates the external state, it means that there can be two functions accessing the same state. So we don't have to synchronize the access. We don't have to do those things around concurrency that we need to do, because I can just call it in parallel. And then they can be lazily evaluated. This means that I can actually call the function and I might have a like return value back. But I don't have to necessarily execute that function until this value is used. And it doesn't have to be used because some logic in the program can tell me that, okay, I will need that value only if some conditions are met, right? So I don't have to care about whether I call the function only in this case and so on. Now you may ask, like every single program does some side effect. Like I can't imagine like real world program without any side effects, or reading input, writing input to an IO, to a console, to a database, to HTTP calls, or whatever. So basically, every real-world program does some side effects. So how you code the pure functions if you need those side effects? And this is a topic a bit more advanced in functional programming, that there's something like an IO effect. An IO effect is a value describing side effect in computation. So it's describing some operation. It's not actually performing the operation. It's just description. And that description is like really overly simplified a function that I can call. So the whole program is just a composition, is a sequence of functions that I can evaluate. And this IO effect can describe synchronous or asynchronous operation. So this is really a simple example. So let's imagine we have a DB call function here that accesses database. So this is returning a string just for demonstration, but in real world, this would access a database. So we're using some database driver and a socket, of course, socket layer. So here's our function that calls the database, right? So I would just call this function and I would propagate it to the database and return a string from the database. So this is directly performing the operation, right? It's executing a side effect. So this makes this function not being pure. Now here we have an interface of named IO. So this is our IO effect. This is really simple version of an IO effect. Is basically just a function run wrapped up in an object. So here we would have like pure function that would return an IO effect. So it would return a function, so a description of that database call. It doesn't execute it. It would execute it only if I run the run that here. But I'm not. I'm just returning an IO. Right? So I can call this as many times as I want. I would always get the same IO. Just a wrapper. So this is an IO effect or IO moment. And this would be executed when I run the program. All the description of the operation would be sequenced and executed by one. At the like functional programming or functional program would just have these descriptions of operations, and then it would interpret them. So it would run the database calls. All right, so let's move on to the immutable data structures. So they go hand in hand with pure functions. So when I was talking about pure function, that they can't mutate data on a heap. So if we had just immutable data structures, we wouldn't have this problem because they can't be mutated, right? So it's like a complementary thing for pure functions that help with the purity. And let's talk about these structures. So immutable, it's a term used usually for something actually called persistent data structures, because immutable is something that can't be mutated. So we might have a list, for example, that once constructed can't be mutated, and there are no ways to add or remove elements or replace elements, right? So this is like purely immutable structure, that the content of the structure cannot be changed. But persistent means that the structure provides methods to alter the structure, but not by mutating it in place, but preserving the previous version and returning the new structure instead. So there are two ways how to implement this. And like the naive approach is to copy everything we have and just mutate the copy. Right? So this is called a copy on write. And as an example, we have a copy on write array list in Java. I never use it because really it's quite limited for the use cases for using this. It's quite limited, and they are normally not used. But for that list, if I add an element to this list, it doesn't change the list itself. It copies all of the elements of the previous list and adds the new element to this new copy of the list. As you can imagine, this is not really performant, or when you look at performance, it's really bad because it has to copy every single element just to add a new element. So there's another way to do this for some of the structures, and it's called structural sharing or reference sharing. They are usually used with linked lists or binary trees. So let's look at these. So the most common example is something called cons list. It contains two elements. One is the head, is the first element, and the second is a reference to a tail, to a list that contains the rest of the elements of this list. So it's like a recursive data structure. So in this example, we have a link, this cons list, which is a linked list. This one contains a head with number 1 and a reference to this list, which contains, again, a head is number 2 and tail is a reference to this list. And this is the head of the last list, and the reference to a tail is nothing. It's like nil or null. There's nothing. Now, let's look at the operation. What I would do if I wanted to replace the first element in this list. So I would call a tail. So on this list here, starting with 1, I would call a tail, which would give me this list here. And I would prepend it with 0. Now I get back this list with 0, 2, and 3, which shares the tail of the first list. So we don't have to copy every single element of this list, right? We would just add or prepend the first list with head 0 and a reference and a tail being reference to this sublist or a list starting with 2. Now this has some implication, like the implementation of some operation has its own complexity. So this prepend operation is constant time. I would just add new element and change and add a reference here. But if I wanted to append something to the end of this list, I would create a new list here, and I would need to change this element. Since it's immutable, I would need to create a new one with the head 3 and reference to my last list, and then subsequently all of the previous lists, or yes, lists. So this is basically an ON, so it's linear complexity. If you look at like mutable lists, and they're backed by arrays, so adding a new element to the list is constant time, I think. So of course, these persistent data structures trade off sometimes the performance for immutability. Here's an example of a tree set. Tree set is a binary tree. So XS is our first tree set, which was fairly balanced. Now, if we wanted to add number 5 to this list, we don't have to copy every single element of this list and add a new one somewhere. We can, as a binary tree, we can add a new node here and this reference would refer to this subtree. So we would actually share parts of the previous list while still the previous list not being mutated. Okay, so this is for illustration to continue with comparing different languages and how they support these features or concepts. At the level 1, there's a mutability of variables or references. So this is a comparison of how different languages do the declaration. And it's quite common to see that the var keyword is used in Java, Kotlin, Scala, even TypeScript, although don't use this one. It's really bad. It just has access or exposes the variable out of scope from the declaration. It's really bad. Don't use this. And there's a difference to immutable references. So Java uses final keyword, Kotlin, Scala, there go hand in hand. It's clear that they've been really they motivate each other. With Rust, this is example because by default variables in Rust are immutable, and this is wrong. Sorry, this should be the other way around. So it actually let mute x is immutable. I have to explicitly say that this x is mutable, and if I want to use immutable, it's just to let x. Now let, on the other hand, in TypeScript, create a mutable reference. Const is for immutable references, and Swift uses let as opposed to TypeScript for immutable references. Okay, so in Java, take for example string. So string is actually a persistent data structure. It doesn't, you can't change the content of the string. So there are some methods on string class that allows to create new strings out of this string. So for example, a substring. And it's the first way how to do the persistent data structure. It will copy all of the letters or characters in the string that fall into this range provided by the substring. So we have a standard collection like array lists, hash sets, hash maps, everything in Java from standard collection library. They're mutable. So if you want to go with the immutable versions, we have like helper functions that would create immutable views out of those mutable collections. So if like collections unmodifiable list, unmodifiable set, map, and so on. But I hate those. I hate those because they lock the collection, but provide actually the methods to shoot yourself in the foot. So unmodifiable list would return back a list interface that, of course, has these like add, remove, and so on methods. But when you call it, it throws an error in runtime. So they're just bad, you know, because not only it doesn't prevent you from doing this, it blows in runtime. So I don't see much point in using them. And the same goes for these constructor helpers in JDK 9 set list map off, where I provide some values directly into the off method, and I get back like immutable list. As I mentioned, copy and write list and set are in Java, but if you want really like good persistent collections, you go for Waver library is a functional library that part of that provides these persistent collections. So Kotlin and Scala are very similar. So in Kotlin, we have Kotlin X collection immutable package where all those immutable persistent data structures, data collection, persistent collections are. And in Scala, they are in standard library. So Scala has a scala.collection.immutable and scala.collection.immutable package. And by default, the immutable package is used. So let's look at some custom data structures. So we talked about product types in the past. So both Kotlin and Scala have a way to declare like in really compact syntax a structure. So in Scala, it's a case class. In Kotlin, it's a data class, so you can just change the case to data and you have a valid Kotlin syntax. Now, by default in Scala, all the properties of this class are immutable. So these are the val references, but nothing prevents you from creating mutable references. As I think Java 16 added records that provide similar functionality. They're immutable. Now I can create a new object of person with some properties. And what's really nice about those data and case classes is that they provide a copy method. And the copy method accepts it's generated by the compiler. So it accepts one or more fields or properties, and I can change their values. And the result is that this value is changed and the rest is copied. So it's similar to these copy on write lists, but now I'm copying a structure. So all of the properties that don't change, they're copied, and what I change is changed. But mind, as I said, you still can define like a mutable properties, then it basically creates a shell copy. It doesn't deeply copy the whole object. So I can change, even though the address here is immutable, I can still change the city here. This is immutable. And if I did that, even though the older Homer is a copy of Homer, if I change the address, it changes for both of them, because the address field is copied, the reference is copied, but it's the same object on it. But imagine if you used just immutable properties in all of the object graphs, then the copy method would actually mean that it's safely copying the structure. Now for TypeScript is really, in a sense, quite a mutable language because it comes out of the JavaScript backend. So all of the objects can be mutated unless you really try hard to. So you can use like a third-party libraries like Immutable.js or FPTS. These contain those persistent data structures that I talked about. Now let's look at some built-in constructs in TypeScript, how we want to achieve some level of that immutability. So this is an object literal. So I define the object here. Now, of course, if this was defined like here, I can freely change any of the fields or any of the keys in the object. and their values, no problem. So how we want to make this immutable? So the first trick is to use asconst. So this is something available in TypeScript. And what's really nice about it, it would make the whole object on all levels read-only. So I wouldn't be able to change Homer name nor Homer address dot street. All of the fields here would be immutable or read-only. As mentioned here. Now we have an object freeze. Now this is, again, this creates like a immutable copy of that Homer object. So the frozen here, the inferred type is same as here. It's read-only, the type of this one. And also it's frozen at runtime level. So even if I bypassed TypeScript compiler by casting to any and back, whatever, if I try to mutate some of the fields here, it would throw an error on runtime. So this is like alternative. I can specify read-only with generic type, which just says that all of the fields of this type are read-only. But this is only a shallow read-only copy, right? So for the Homer here, I still would be able to change city of the address. This is only on compile time. But using like the fancifully TypeScript compiler should pose no problem here, because it should not be possible to change it without bypassing the compiler. Now, if we have these read-only structures, how do we copy them? So we can use the spread operator, which copies all of the fields, and I can replace some of them, right? So I would create a new version of, well, new object with all of the fields copied from the Homer object, and the name would override this Homer name here. So it's the same thing like the copy on write approach. Similar for arrays. I can use the spread operator and copy the content. All right, and this leads us to the last slide here. I was looking at Rust. There are crates with, well, crate is a package or a library in Rust ecosystem. And there is a IAM crate that provides these persistent data collections. However, due to like special Rust memory model, they're usually not needed. So I'll leave you with these citation from the Reddit user that in Rust, if some stack frame of a program is able to mutate some data structure, that means that no other frame possesses a reference that can observe the mutation. So this basically solves most of the problem with mutable state being able, or some structure being able to be mutated by different parts of the program, which can lead to bugs, of course. And I think that's all. So thank you everybody for your time and attention. And if you have any questions, then go ahead.
I have one, if I may.
No.
Can we get back to your definition of pure functions, where you mentioned also the exceptions?
Yep.
So you're saying here, based on this definition, means that each and every function that can throw an out-of-memory error is by default not pure function?
Yes, and this is a really good point.
Because, you mentioned a couple of use cases when we do the copy and we return the copy and similar stuff, it could still be pure, which means that, every time we work with the memory, the out-of-memory error could be, could be thrown by the internal business logic of the function, which makes it impure.
Yes, and that's exactly right. So every function, in a sense, that does anything with memory access can throw out the memory error. So this would make, by definition, make all of the functions impure.
Yeah, that sounds good to me. That's what I wanted to hear.
Yes.
Sometimes some functions are considered to be pure, even if they can work with the memory, which makes them impure.
Yeah, right. So I would argue that you don't handle out-of-memory errors. You just let it crash your program. Really, there's no recovering from it. So when it comes to program and the logic around handling exceptions, handling out-of-memory errors is a bad thing. You don't want to do this. You just let your program crash. So
yes,
in this sense, these functions are also not total, right? Because they don't return. So this is a really like more like a philosophical question.
Yeah.
Because, well, in reality, we talk about functions when your program executes but not crashes the whole program.
Yeah, makes sense. Because this definitely conflicts with the thing that the function always return the same result. There are use cases where it does not return anything because of the out of memory.
Yes, and you're exactly right.
Cool. Then do not know whether I remember all my questions, but can we go to string object in Java? You mentioned. Was it considered to be immutable in that? In this kind of definition you mentioned here?
Yes, it's immutable. It's persistent. It retains the previous thing. It retains the previous.
So my question is, does it mean that each and every object that its internal member variables in Java are not changed, does it mean that it is immutable? And if some member variable internally is changed, then it is mutable because we mutated the state of it.
Yes, that's by definition.
Okay, then if you will use this one, then I would consider string to be mutable as well. Because if you look at the hashcode function in the string, the default value of the member hash is equal to 0. Until you do not call the hashcode, it is not calculated, and the hash is always 0. Which means that first time you call hashcode, the internal state is mutated.
Okay.
Which by this definition, it makes it mutable.
Well, I don't think that this is about like mutating internal state, but being able to basically share that state with, because you can internally like optimize. Of course, you don't want to calculate the hash if you don't want to. You can mutate it internally, but it's not visible to anyone.
So yeah, so that that's what I'm pointing at. That this definition, it's not fully correct if you just say that the internal state or member variable values are not mutated, because they can be mutated, they can be changed, and until it is not visible, and it still can be considered as immutable.
Yeah, I agree. So I would just maybe change the definition that internal state is not observable to be mutable.
Yeah, that sounds good to me.
Something like that.
Cool, and that's it. Probably what I wanted to ask.
Thanks. Definitely good questions. Anyone else?
I have one question regarding Java and collections. You mentioned that by default, the standard collection in Java, everything is basically mutable. But if you want, you can use this Waver library. My question is if you ever use that in some real world project and if that is used overall.
Use that. Yeah. Yes, for me personally, I used it. It's part of our internal project scope tracking tool, actually. So I can show you some examples later. Well, with the collection, with the library, there's these things that all your method signatures would need to change their collections, right? So, because they're not interchangeable. Of course, I can't use Java util list. I want to use like Waver list. So all my code base then changes like from Java util to collection from Waver, and they propagate, and then you need to access some libraries that don't use these, of course, that don't want to depend on a third-party library. So you have to like transform back and forth. So even if there is like a good solution for that, it's not that like straightforward, and it's blows the code a bit.
Mm-hmm.
But of course, these collections already provide some mechanisms for transforming from Java collections and back.
Okay. I consider this as answered. Thank you.
Okay, thanks. All right, and I would just say one more thing, that having mutable state, it's not bad. It's actually a good thing when you care about performance. Definitely those mutable collections or mutable data structures always win in performance. But my advice is to restrict the mutable nature of the code within functions or within methods. Don't expose it outside of your class or a function, because this would like leak this mutability out of the function, and it's a source of bugs. So really, if you want to answer why do you want to call with pure function immutable data structures, I ask you to think about when you come across a bug, not only like reported by the user, but during the development. Think about whether this could have been prevented if we used immutable data structure or in pure function. So my approach is to use the mutability within the functions, but don't pass it around on stack, right? Because quite often they lead to bugs, because some state mutates and some other function, which might be like far away from the actual change, depends on that, and it's not quite visible in the code. So just do your maybe analytics on why a bug, or during development why there's something not working, whether it might have to do something with mutability, and quite often it will. All right, cool. So unless there's anything else, I think we can wrap it up for today. Thank you, everybody.
Okay, thank you.
Thank
Bye.
you.
Thank you.
Thanks, man. Cool.